Thank you.
Okay, I think this started already. All right, so this is a rather short lecture. It's all worked out that way because I knew I was doing all sorts of stuff today. So hopefully you know a lot of this already because we've had labs related to these kind of things. But we're going to talk about sharpness, magnification, and shape distortion. So let's talk about it. We'll hide that. So spatial resolution is an important aspect of every image. It's really important because it's related to the sharpness of the image. Later on, I'll tell you up front anyway, there's a nice little definition for spatial resolution is the ability to distinguish objects that are in close proximity to each other. A lot of times I talk about it as if you go to the beach, not on a day like today, but I guess you still could, and you pick up some sand, and if you can tell the particles, and there's like a little spacing in between to maybe count the grains of sand, that would be really, really good spatial resolution. If they kind of start to clump together, then spatial resolution is getting worse. I'm not talking about being able to distinguish the shade of one grain from another. That's contrast. Spatial resolution is more of a quantity thing, being able to quantify an object. Sometimes you'll see a question on a test coming up eventually, like how small of an object can be resolved if you have a system that has certain things that we didn't learn yet, right? And obviously the smaller that you can resolve an object, the better it is for the patient, because if you can't resolve an object and you can't see it, identify it, and you have a misdiagnosis or no diagnosis, who knows? And a lot of times we look at spatial resolution, as you've seen in the labs, by using a line pair test tool, right? The more lines that you can see, the better. So spatial resolution is better here at, let's say, 0.8 than it is at 1. And then we're starting to lose it. So an object that's 0.6 millimeters will not be able to be identified, right? That's kind of what that's saying. So, sometimes we call it sharpness, but spatial resolution is the technical term. Sort of the opposite of spatial resolution is blur. We've talked about it before in terms of penumbra. It's kind of like the unsharpness around the image. If you take a flashlight, I guess, and kind of put it against the wall, let's see if I can try this here somewhere. Kind of see the blur around the edge. Not as distinct as the middle. Right, that's kind of the penumbra. And the middle of that, now the closer I get, the more sharp it is, but you can actually see the penumbra too. So the middle is called the umbra, and the part around it is the penumbra. Right? I think we've talked about this before because I remember mentioning like solar eclipses and things like that. So you're going to see in a couple seconds that there are there's like 3 different calculations in this. So next quiz, math. Or actually, I think this is on the big term too. Magnification is just when the object gets bigger. Right? We don't usually like magnification. It falls into a category we call distortion, and we don't like distortion. So when things are magnified, they tend to be a little blurrier. So there's a little bit more penumbra. Sometimes magnifying something is helpful, just to kind of see something that you might not have seen before. I know it sounds counterintuitive, but the sharpness increases when magnification decreases. So we don't really like magnification most of the time. Some of the things that affect magnification that we've talked about in the lab or that you may have read about already is SID and OID. So when SID is decreased, magnification increases. So that's why we like to have a longer SID rather than a shorter SID. And when OID, it's the opposite. When OID increases, so OID, if you remember, that's the patient to the image receptor, right? So you want to lower your OID, right? You want the hand right on the IR, which would reduce the OID, which would reduce magnification. So magnification increases when the OID increases. Then there's shape distortion. We haven't done this in the lab yet, for sure. Shape distortion is different from size distortion that we've been talking to up until this moment. Shape distortion is when the actual shape changes. So something that looks like a circle turns into an oval, or something that is generally long gets foreshortened. When it comes to shape distortion, there's two types. There's elongation, things get stretched out, and then there is foreshortening, things kind of get squished together. By the way, in magnification, so I'm going kind of stepping back for a second. In magnification, all parts of the image are kind of stretched out. So magnification is uniform. Elongation happens only in one direction, right? So in terms of elongation, if you angle the tube, you get elongation. So if I angle the tube this way, that part of the object gets stretched out. If I angle it the other way, it gets stretched out. Usually in the department, you're either going caudal towards the feet or cephalic towards the head. You're usually not taking the X-ray tube and pointing it towards the door or towards the wall that way. But that would still create elongation. Shape distortion is tough, right? Because it makes things look very different. It's a lot worse than size distortion, right? Size, people can get a grip on size, right? It just gets a little bit bigger, a little bit smaller. Shape distortion is tough. And it's tough to position for because your organs are at different angles inside of your body. There's only so much you can do inherently anyway. So look at this cube turning into a rectangle. Okay, so can we measure this stuff? Yes. Is it based on some things that we can quantify? Yes, some easier than others. So we have some terms that we've already gone over. We have your, we have your source to object distance. That's from the source to the object. So from the AB to the X. You have your OID, and we said our OID is from the object to the image receptor. And it's not shown here, but we also know, just for the record, SID is from the source to the image receptor. And in this particular slide, we're showing that things can actually end up being somewhat proportional. Here we have an SOD of 38. So that's this part. And we have an SOD of 76 inches. That's this part. And here we have 2 inches OID versus 4. But we end up, if you look at this, we both have an unsharpness level of 19, which means the penumbra for both of these are going to be the same. I didn't tell you that the object is the same also. I mean, that would have thrown things off, the object itself. So formula number 1. Unsharpness, also known as penumbra, which is why you have to know that if you're solving for unsharpness or you're solving for penumbra, it's the same thing, right? So you need 3 things to quantify this, right? you need your focal spot size, you need your OID, and you need your SOD. And guess what? Can you figure out your SOD if it's not given to you? You can, right? Right? Because SOD is your SID minus your OID. Don't say that too many times fast. Right? So why am I telling you this? Because I might not give it to you one day. And you'll just need to know that, well, oh, look, the SID is there, and the OID is there. If I subtract, I'll get the SOD. So this is the amount of unsharpness penumbra. We said it can be calculated by using the focal spot multiplied by the OID divided by the SOD. It's phasoid over SOD. Yeah, I don't know, whatever. The problem with not this particular question is the formulas all use these, not all of them, the other one doesn't use focal spot, but a lot of them have the same terms with SID in it and SOD, and it can get really confusing. Letting you know in advance. So here's one, let's try this. Given a focal spot size of 1.5, here's the 1.5, and an OID of 30 centimeters, and an SOD of 60, we do all the math. We end up with 45 divided by 60. Remember the whole PEMDAS thing, right? You got to do the correct math, right? Does anyone not know PEMDAS? You do the thing in parentheses first, and then exponents and multiplication, division, right? Yes, yes. I have a whole box of calculators. They're not really fancy ones, but we have them. And I'll start to, so yeah, it's a good point. You can't use your cell phones for this stuff. Or your own, just because you like your lucky calculator, you can't use it. Okay, so this one, we get the penumbra spreads across an area of 0.75 millimeters. That's really small, right? That's not even 1 millimeter. Right. So chances are you wouldn't really notice this too much in real life, but sorry, it's on the test, so I got to teach you this stuff. Okay, then we have the radiographic sharpness formula. And this one is particularly useful when you're comparing multiple exposures, like exposure A versus exposure B. And this one does not use the focal spot. Okay? And it's based on the ratio between the SOD and the OID. Okay. Again, if I give you SID, which is not part of this, but if the SID is in there, you can figure out the SOD. If I don't give you, I got to give you at least 2 out of 3 things, right? I mean, if I only give you one thing, then you can't do any of these problems. But so exposure A uses an SOD of 90 centimeters. There's the 90, and an OID of 5. If the SOD is changed to 180, so this is like another scenario. So exposure B, if the SOD is changed to 180 and the OID is reduced, what is going to be, which one's going to be sharper? Which image is going to be sharper? So we get the ratio of this. The way we do that is we take 72 and divide it by the 18, and we get a number 4, and we find out that exposure B will be 4 times sharper than exposure A. And you can try to test this with the line test pair tool and see if it's better. Right? How are we doing here? So here's a line test tool. We have 5 minutes or so. And it's useful, right? We've all worked with this, so I'm going to keep going. So here are our variables that will affect sharpness. We haven't talked about motion before, but you probably have taken a picture where the object in front of you moved and everything was blurry. Same thing in X-ray. This is why we tell people to not move or hold their breath or tie them down when necessary in a nice way, right? So sharpness can change based on motion. Obviously, you get blur. It's actually sometimes known as false images that kind of overlap on each other, but end up looking blurry. Sharpness, as we have done in the lab and we've been discussing, will be affected by what we call the geometry of the beam. So things like SID, SOD, and OID. A few weeks ago, seems that long already? Feels like we just started. A few weeks ago, we were talking about the focal spot size has an effect, right? Smaller focal spot is better. Size of detector elements, we didn't talk about this, but that will also affect things. And how good your monitor is, right? You can take your Toys R Us monitor, if Toys R Us existed anymore, and you could base it on, one monitor is better than another. Right? Anyone buy a TV recently? That's one of the things you kind of look at. Or cameras, right? You want more megapixels. The more megapixels you have, the better the sharpness is. I remember my first digital camera. A lot of you might not have been born yet. I think it was 1.6. That's it.
Megapixels.
Yeah, that's it. Now what are they up to? I don't know. 20?
The most recent one was 34.
34. There you go. See, I don't even know. Right. But it was digital, so it was still cool compared to like film, where like, I remember my father saying, you can't take that picture. We only have 24 exposures. Are you kidding me? Now you let the kids play, kids play with phones and cameras. So magnification, as I was saying before, both the length and width, everything gets magnified in a uniform way. That's what this is saying. There's always going to be some inherent magnification also. So let's back up for a quick second. OID creates magnification, right? So if we're doing a forearm, we want to put the forearm as close as we can to the image receptor if it's this dense. But my skin and muscle is in front of the bone. Now, unless I carve it off, which is not very nice, I'm going to have inherent magnification built in, right? Just because of the skin and muscle around any particular bone. So even if I get really close up, as far as I possibly can to the IR, I'm still going to have some inherent magnification. Oh, I have one more. Okay, I think this is the last one. Magnification formula in pink. As long as the distances are known, magnification can be figured out by the ratio of the SID to the SOD. Right. So let's try to do this. Oh, look, I even put this one here. That's right, I've already mentioned that a few times. So magnification is going to be equal to the SID over the SOD, and we can also, if we know the image size versus the object size, guess what? We've done this in lab like 2 or 3 times already. We just never really talked about it. So an object measuring 40 centimeters in width is radiographed. So that's the object. Is radiographed using an SID of 100. So here's 100 and an SOD of 60. Here's our object, right? So you're left with one thing to figure out. What is the magnification going to be of the image? I'm telling you, the hardest part about all of these things is remember the formulas, right? We don't do crazy math. It's usually solve for X. So let's do that. Yes, you're going to have calculators. So you don't have to, cross out zeros and try to make the equation easier. Just do the math, the way it is. So we get 40 times 100 is 4,000, 60x divided by 60, and we get the image width is 66.7, right? It's always going to be higher than what you started with. So you should be able to eliminate at least one answer on a test, right? Because there's always going to be some inherent magnification. right? So automatically, if you get a number that's lower, then you did your math wrong, right? So keep that in the back of your head. That's a pretty big difference, though, right? Whoops. So we mentioned shape distortion already. It's either going to be elongated or foreshortened, right? So A and B, that is size distortion. C, the whole shape is changing, right? And again, you can't control some of this stuff. We position the patient in certain ways to try to reduce all of these things. But, you know, when you have an object that is in your body and it's going from, you know, my belly button diagonally towards my back, and I lay the patient, you know, just supine, you know, that object in there is still going to be like this, right? To get foreshortening, I talked about elongation before. Foreshortening will occur when the object is not perpendicular, I should say parallel to the image receptor. So if this is the image receptor here, okay, this is the way you want it to be. But if the object is like this, it's going to get foreshortened. You can actually test this out. If we had time, I'd make you all do this. But you know, if you look down at it and then you tilt it, your fingers get closer together when you're looking straight down. Not much you can do to remove shape distortion, except try to keep the object parallel, and to reduce elongation, try to keep the tube perpendicular. Those are basically the rules. Unless you are trying to remove anatomy, right? We do angle sometimes because we want to get superimposition out of the way. So last two. Resolution, we've talked a little bit about, and here's that definition that I mentioned, the ability to distinguish two objects that are in close proximity to each other, right? You know, if we went back, so I know I'm wasting time, but if we went back to this, right? This is not good, right? Even though you can see the lines, because if you had two objects in between these two lines, right, in that space, then you wouldn't be able to tell them apart. Okay? The closer the lines are together that still have a space, then you can theoretically separate one object into one line pair and the other object into the other. If they're both small, it doesn't work that well. It's kind of like this. If I have an object here and an object here, I can't tell them apart. They all fit in that one line pair. If I have more line pairs, making my spatial resolution better, theoretically, it becomes something like that. And now I can potentially separate them apart from each other. I like this image. Because it's everything that we kind of talked about, right? So there's nothing really to go over other than to say that it's kind of cool. And that resolution can be broken up into these two kind of pieces, the visibility piece versus the recognizability or geometric stuff. And geometric falls into magnification, like size distortion, sharpness, shape distortion. Visibility is noise, contrast, and brightness. If the contrast is really bad, then your spatial resolution may be hard to see. It might be there, but hard to see. It's kind of like I could have like great spatial resolution, but if the image is black, I'm not going to see anything. Right? So that's kind of what this stuff is. Okay. Study. I know I went over, or did I? By 4 minutes, maybe? Not too bad.